All right, hi. This question was requested. It's from the 2019 PAT. It's question 19, as you can see. So in the question, we've got a firework that is launched vertically, which explodes whilst moving upwards with a vertical speed of 2 meters per second. The explosion releases some energy, and the rocket bursts into 4 pieces with masses 1, 2, 3, and 4 grams respectively. Tells us mass 4 is going to move vertically upwards at 1 meters per second. So that's actually slower than it was going initially. 3 and 2 move horizontally, that's important, and M1 moves vertically. So all directions, velocities are given relative to the ground. Your answer should do the same. Obtain the speeds of the pieces after the explosion. There's different ways to approach this, and you could do this in terms of the frame of reference of the center of mass, but I'm not going to do that. I don't think there's an advantage to it, especially given that M3 and M2 move horizontally. So let's think about what's happened here. We have a cluster of masses, 1, 2, 3, and 4. All moving upwards at a speed of 2. They explode, and after explosion, I've got 3 and 2 are moving horizontally. I don't know which way around they're going to be, and I don't know how fast yet, but they're moving horizontally. So importantly, they have no vertical velocity whatsoever. M1 is moving with 1 meters per second up. Sorry, M4 is moving at 4 meters per second. I'll get there in the end. M4 is moving at 1 meters per second upwards, and we're trying to find the speeds of the other pieces. So M1 is traveling at some unknown velocity. I'm going to call its velocity V1. And since we're taking up as the positive direction, because this was positive 2, this is positive 1, I'm going to say that V1 is an upward velocity. If we get a negative answer, that's just going to tell us that it's moving downwards. So finding the speeds of all of these objects, the first thing I'm going to do is just straight up conservation of momentum. So initial momentum is the total mass multiplied by 2 meters per second. The total mass is 1 plus 2 plus 3 plus 4 is 10 grams. Times 2. That must be equal to the final momentum. Now, what I'm going to do here is just bear in mind that 3 and 2 are moving horizontally. So they, in the vertical sense, they have 0 momentum. So let's do this vertically. The initial vertical momentum is P, is that. That must therefore be equal to the upward momentum of mass 4 times 10 to the minus 3 times 1 plus the upward momentum of mass 1 times 10 to the minus 3 times V1. As we can see, the times 10 to the minus 3s are all going to disappear out of this, so I can write this as 20 equals 4 plus V1. V1 equals 16 meters per second. So that's got the first one. The next thing I need to do, I need to find the speeds then of 3 and 2. I know that they have no vertical momentum, but they're moving horizontally, so they have horizontal momentum. And what I can say is that their total horizontal momentum must sum 0, because initially the whole thing was moving vertically. So the initial horizontal momentum, P equals 0, that must be equal to, I've chosen 3 to be going to the left and 2 to the right. It isn't going to matter which way around you do that. We're only after speeds here, because what we're after is a relationship between the speeds, between the velocities of 3 and 2. So it doesn't matter which way around we choose these. That must be equal to 3, again, times 10 to the minus 3 times V3. Sorry, let's make that, yeah, V3 will just be a negative, I suppose, plus 2 times 10 to the minus 3 times V2. So by conservation of momentum then, the 10 to the minus 3's I can cancel out, and I can say that 2V2 equals minus 3V3. So I've got this relationship between those two. The next thing I have to do then is think about energy. Let's conserve energy in this setup. So in terms of energy, the initial KE is a half times the total mass, which is 10. Oh, hold on. Half times 10, and again, this is all in grams, times 2 squared, because it was moving upwards, remember, at 2 meters per second. That's the initial kinetic energy. The explosion itself produces 1 joule. So therefore I can say that the final energy must be equal to this, so a half times 10 times 10 to the minus 3 times 2 squared plus 1, and that must be equal to the sum of the kinetic energies of these kind of fragments of firework. So that's going to be equal to a half times 1 times 10 to the minus 3. V1 was 16, plus the other one that we know is V4, that was given in the question. V4 is traveling at a speed of 1. Plus then the kinetic energy of the two unknowns, half times 2 times 10 to the minus 3 times V2 squared plus a half times 3 times 10 to the minus 3 times V3. Oh, no, not V cubed. That would be horrific. V3 squared. Okay, now this equation then, let's get rid of all the times 10 to the minus 3's and all of these halves. So let's multiply through by 2 and by 10 to the 3 and get on this side then 10 times 2 squared is 4 plus 1 becomes 2000 because I'm multiplying through by 2 by 1000 equals 1 times 16 squared plus 4 times 1 squared plus 2 V2 squared plus 3 V3 squared. Now at this point, all I need to do, hopefully, is sub in from my conservation of momentum expression, sub into this conservation of energy expression and get something neat. So let's actually do the maths here. I've got 10 times 4 is 40. So I've got 2040. 16 squared is 256 plus 4 plus 2v2 squared plus 3v3 squared. 260, that's 1780. So if I look at this expression that I've got up here, if I rearrange this a little bit and square both sides, I can say that V2 squared is equal to 9 over 4 V3 squared. Obviously squaring the minus sign is going to disappear. So here then 2v2 squared is equal to 9 over 2 v3 squared plus 3 v3 squared, which is equal to 15 over 2 v3 squared, and solve for v3 then. This is a calculator paper, I hope, because I'm not seeing a straightforward solution to that. So I haven't actually checked. I'm assuming this is a calculator. I'm not going to bother writing out the thing. I'm just going to tip it into my calculator now. Hold on. Where are we? 1780. 15.4. Yeah, that doesn't look like it would have come out in any way from mental arithmetic. So hopefully this is a calculator paper. Then I can get v2 as well using either expression, using whatever. So v2 then is equal to, don't go to sleep. 23.1. And that's it, I think. So we've got v1 up there, we've got v3, and we've got v2. Yeah, so that's the first part of the question. The second part, higher speeds can be obtained if the directions are different. Under which choice of directions would the maximum speed of one of the pieces be achieved? So no calculations are required here. If we just think our way through this, we're going to share out 1 joule of energy between these 4 objects that are all traveling upwards at a speed of 2. If we think about it, the way that it has happened initially, where I have 2 going kind of horizontally, if I think the best way I can share out that energy to achieve a maximum speed of one of the objects is to have all of that energy happen in a single direction. So we want all the kinetic energy to be working in the same direction. So we want 1, 2, 3, 4 all to be traveling in the same straight line. If I also think about conservation of momentum, if I am having them all separate out into the same straight line, then what I want to achieve a maximum speed, the smallest object, the one with the least mass, is the one that can achieve the most speed. Because if I have, from this initial setup, if I have 3 of them go in one direction and 1 of them go in the opposite direction, the one that goes in the opposite direction has a much lower mass than the combination of the others, so it will be traveling faster than them. If that one that goes in the opposite direction is the one with the smallest mass, then it will have the highest possible velocity. If we then add to that the fact that it starts off moving upwards at 2 meters per second, it makes reasonable sense then that if I split these such that 1 is traveling upwards and 2, 3, 4 are all traveling downwards, then none of the energy released in the explosion is wasted sending stuff out side to side, and by conservation of momentum, 1 will achieve the highest speed upwards, because the total mass going in the opposite direction is substantially larger. So if you think about it, this has a total mass of 9 and this has a total mass of 1. So the 1 gram mass here will be traveling 9 times the velocity of the others away from the center of mass, which is already going upwards at 2 meters per second. So that is the arrangement that is going to get us that maximum speed. How you kind of describe that in some detail for 3 marks, I'm not really sure. You'd want to make reference to the idea that none of the kinetic energy has been used to move things horizontally. So in that way, you're maximizing the use of the energy, and then make reference to the idea that by having the maximum amount of mass move away from the smallest amount of mass, you get the biggest speed difference. And then for the third mark, I guess, make reference to the fact of, since it's already moving upwards at 2, you would want the small fastest particle to continue moving upwards to give you that maximum possible velocity. Alrighty, hope all that makes sense. Sorry it went on a little bit longer than I'd planned, but hopefully that's useful. Cheers.